let's make a start on that then. So the maximum min stuff. Did you end up actually having a look at the rest of the example in this one?
No, I did not.
No, that's okay. Cool. Do you want a refresher on any of it, or do you want to just dive straight into the questions?
Can we have a little bit of a refresher?
Refresher? Sure.
Yep.
So finding the maximum or minimum of a certain function. Very common question that comes up literally every single time. It'll be basically guaranteed on your exam. Probably both in the tech free and the tech active will have some sort of version of this. We've done very similar questions like this before, and we're trying to find like the maximum area of a type of shape. We will be doing the sort of parabola sketch, looking for the peak of that parabola, and then going from there. Basically, now that we have access to differentiation, we can use a derivative to help find those turning points. And that's the gist of what ends up being the case here. As for like an overall procedure of things, typically you start by creating the expression for the thing you are trying to maximize or minimize, whether it's area, volume, length, those are the common ones. From there, if you're tech-free, you'll be doing derivative equals 0 to find the stationary points of that function, because one of those will definitely be the maximum in tech-free. Tech-active, it may or may not be a turning point, so you'd use your fmin or fmax in the CAS instead. And then, yeah, sometimes it just requires the x value of that, in which case you're fine to just leave it at solving the derivative or using the fmin or fmax. If you need the actual maximum or minimum, then you'll sub that back into the original function that you've created. So let's see how that looks. In this case, we have the trapezium example here. We're trying to find the value of x4, which maximizes the area of this trapezium. Step one, as I mentioned, was creating the area formula for the trapezium. So we start with the basic version of it, maybe label our terms accordingly. We'll notice that we have A immediately and we have B immediately. What we don't have is the H. There's no corresponding letter or number associated with it. But because it's part of this triangle, we can use a bit of Pythagoras and then get that H value purely in terms of X. Right, this is our hypotenuse. So basically the A squared plus B squared equals C squared thing, and then just rearranging as necessary. Put it all together, you have your area equation. In this case, I'm doing it through a tech-active approach, so we're just going to use fmax on it, directly giving us the x value for which there is the maximum. That's all it was asked in this case, find the value of x which maximizes. If it said instead, find the maximum possible area, you would then shove that back into the function. Cool so far?
Yep.
Sweet. In a tech-free way, you would have to go through a derivative approach rather than fmax. So starting with our area formula, just simplify things down a bit nicer so that we can actually use it a bit better, because we do have to do it by hand at this point. This is a product of two terms, so we're going to use the product rule. U equals 2x, v equals the whole square root. Diff them both. This is going to be a chain rule because you've got the composite function. Plug it all in, and this isn't particularly nice to look at, but turns out to be the case that it won't end up being so bad when you multiply both sides by this denominator for solving derivative being 0. Multiply both sides by the denominator, that's going to disappear, this root's going to cancel out into just the inside, and then you're just solving a quadratic like you normally would. From there, simplifying the roots down, and also rationalizing whether or not you use the plus or the minus. So that would require you to go back and figure out, okay, what is x actually defined as? Well, it's these lengths here. Lengths can never be negative, so we're only going to take the positive solution of that root. And then, yeah, that's your final answer. If you did have to show it back into the function to get the area rather than the x value for which there is the maximum, then the solution might look something like this, as far as how you would go ahead and simplify it, just slowly breaking down the factors over and over again until you, well, fully simplify. There's a bunch more examples. Would you rather me go through more examples, or should we start tackling some of the textbook stuff? If you answer me, you're on mute.
Oh, sorry. These are just optimization questions, right?
Yeah, yeah, that's the other term for it. Optimization questions, finding the maximum or
Yeah.
minimum of a thing.
Okay. So can we do the textbook questions?
Yeah, certainly. Let's see if we can find a decent one. Okay, so question 1 we've done to death in like your polynomial stuff. I believe these have also come up enough. Maybe something like question 5 is where it's a bit more unique to this chapter section here. What do you reckon? Start at question 5, or have you done that enough times?
Yeah, we can do question 5.
Yep, let's do it. Okay, we got this equation, find the values of p and q that make z a minimum. So that's a bit odd. Normally you'd get like one variable in terms of another. In this case, we're actually getting two variables controlling one. That's a bit interesting. Let's see how we go. I'll start writing out the relevant stuff, and in the meantime, have a think about how we might start. The values of p and q that make z a minimum. What might we do?
Um, uh, should we try and isolate P or Q from the P cube Q equals to 9?
What do you want to do with it, sorry?
Like, can we make Q the subject in P cube times Q equals to 9?
Yeah, we can make the q the subject, yeah?
Yep.
It's going to give us q equals 9 on p cubed. Cool.
We can substitute that into the second equation.
Yep. Z equals 16, so we're still going to have the p there. And 3q, so q is that. 27 on p3. Nice. All right.
Okay, so we have to find a minimum.
Yes.
So this is going to be cubic. We can find the derivative of it. So
Yep.
16 plus, can we simplify the equation first? So 16p equals to 27 times p to the negative 3.
Yeah. That's probably a good idea. Getting a negative index there makes it a lot easier to see what that diff's going to come out to be.
And so 16 minus 81 p to the negative 4.
Yes, negative 4. Good.
Yep.
Nice.
Okay. Yeah. This. Um, can we graph this? Is this a tech free?
Tech.
Yeah, this looks to be tech free.
We'll make it tech free. They tend to be a bit bad about whether it's tech free or tech active. This one I'll say should be pretty solvable tech free.
Okay. So. Okay, we can look at the original equation and we can try and find the behavior. So 16p plus 37p to the negative 3. Wait, no, that's Oh yeah, that's right. Yeah.
Yeah, doable, but it'll take a bit of effort to figure out how you deal
Yeah.
with the cube on the bottom.
Yeah. I forgot how the negative odd powers work.
Yeah, so those are like your hyperbola or truncus type looking graphs.
Okay.
So your 1 over x with any odd power is a hyperbola, with any even power is a truncus.
Okay. It it applies to negative values as well.
Well, yeah, because like x to the negative 3 would just be 1 over x cubed.
Oh yeah, yeah. Totally forgot. Yeah.
Yeah.
Um. Okay. So cubed. That's a hyperbola.
Yep. So it's going to be hyperbola shaped. That's right.
Yeah.
So that term specifically will be something like this.
Yeah. Yeah. Okay. Hmm. Um. Minimum. Yeah.
Mm-hmm.
Um. Yes, there. The the derivative will be a truncus.
Yeah. Yeah. So derivative will let's see what we can do there. It's got some negative to it, and it's shifted up by
Okay.
16.
Yeah. It's okay. It's getting hard to visualize it.
Yeah, yeah.
Yeah.
Part of the issue, I think, is you might have forgotten to include a 16p in this as well, because z, the original function, is not quite just a hyperbola type shape. It's
Yeah.
also
Yeah.
got a linear in there. And so what you essentially do is overlay the two of them together and do... Have you done addition of ordinates yet? The chapter 1 thing?
Addition of ordinance. Yeah. Yeah.
Yeah, so you do a very similar... It's actually exactly the
Yeah. Yeah.
same.
I think yeah. I do remember.
Yeah, so you kind of get... It ends up looking kind of like this now, where you on the outskirts start matching the linear, but on the inside you end up with these little turning points in there. Um, so that makes it a bit easier to spot that the minimum is going to be over there because all of this is invalid, right? We can't have negative x's or, well, I guess, hang on a minute. They're positive quantities as per the question, p and q. So we can't have anything on that left-hand side.
Yeah.
Um, so we know roughly where it's going to be as far as like what quadrant it is.
Yeah. Yeah.
That'll more so help us when it comes to solving our derivative. Because the whole point of the derivative was what?
To find the turning point.
Yeah, to find turning points or
Yes.
stationary points. So now
Yeah.
we know,
So
yeah,
we can now find the derivative equal to 0
yeah,
because
that's it.
that's when it's going to like change um the thing.
Mm-hmm. Yeah, exactly.
Yeah.
Derivative 0 will find
Yeah.
that point.
Okay. So 16, you can take it to the other side. 8, so negative 81. Yeah, that's up. Yeah. Hmm. So 81 over 16,
Yep.
and you can take the 4 to the other side. That makes it 3 over 2. No,
Oh, hang on.
the
The final answer ends up coming out
yeah,
to 3 over 2, does it? Yeah.
yeah.
Sick. So you get the plus minus 3 over 2, but we already kind of know
Oh
it's going
yeah,
to be the...
plus minus.
Yeah, but
I keep
you already know it's
forgetting
going to
that.
be the plus as you said anyway, because it has to be the top quadrant.
Yeah.
So yeah, sick. That's going to get us the p equals 3 over 2. Nice. What else do we need to do? Or is that it?
Um, I think I get the concept.
Yeah. Okay,
I think I
so as far
understand
as
how to use it.
say again, sorry.
Yeah, I think I'll be able to use it when it comes up.
Oh yeah, no, I meant as far as the rest of this question goes, just finding p wasn't quite the end of it. It
Oh
said
yeah,
finding the
yeah,
values of p and q,
yeah.
but
So
going from there
yeah,
not too much.
yeah. So we just substitute the value back into the Q.
Yeah,
So
so you got the p value. You'd probably use this one of these equations here to get
yeah,
the other one. Yeah, that's it.
so Q equals to 9 over P cubed. So
Yep.
9 over 3 over 2 cube.
Yeah, and then
So
whatever
that's
that
going to be
simplifies
like
down to.
9 divided by 27 over 4. Wait, no,
8.
8. Yeah, 27 over 8. So that's like 9 times 8 over. Wait, I'll just write it.
Yeah, yeah, that's fine.
Write it somewhere. Yeah. So it's 8 over 3.
Yeah, sweet. That's our P, that's our Q. Did they want us to say anything else? No, they just wanted to get the values of P and Q there. So yeah, even though it was a complicated function, we had to do a bit of addition of ordinates to figure out what the graph ends up looking like. We didn't technically really need to, unless we wanted to validate that it definitely had a stationary point. In tech-free, you can very safely assume that it's going to have a stationary point there. So as far as like minimum required to get to the end goal, it'll be rewrite this equation, shove it into the z, diff equals 0, and then shove that result back in at the end. It's a very standard procedure for the tech-free version. Sweet. Okay. Let's see what else we got here. 6 is probably more similar to what you'd already be used to. Yeah, it might be easier if I just let you pick one out of these if you wanna see anything specifically, or if you just kind of want to keep doing a bunch of them.
Um, N looks interesting.
Which one,
It's
sorry?
got the diagram.
Oh, 10.
10.
Yeah. Yeah, that's where we get the trapezium related stuff. You've now got thetas involved, so something trig related, surely. Alright, let's suss that out. Okay, find BC in terms of theta first thing. So BC is that top of the trapezium.
So A, B, C, D, trapezium. Okay, so BC in terms of theta.
Mm-hmm. So one of the first things that I'd probably start thinking about would be, well, BC is a length and theta is an angle. So we need to start figuring out how can we possibly just vaguely get angles and lengths related to each other in the same statement or equation.
So I'm thinking of like visualize it. I'm thinking of like drawing a line from C to the line segment of A and D at a 90-degree angle.
Okay, yeah. So straight like this.
Yeah.
Yep.
Yeah.
That's good.
So you can figure out the um, x and y value. So okay,
X
that's
and Y
4.
being like these.
Yeah. Yeah.
Yeah,
I
sure.
mean, side to side and up and down. Yeah.
Yep,
Or
that's
yes
good.
and no. That's what I was thinking of. Yeah.
Well, that's great.
Anyways,
You can do that from
yeah.
here. So how do we
Okay,
get it?
so you have to use silent pause.
Yes.
So you also have to use the Pythagorean theorem.
Maybe. Pythag would
Okay,
relate
we
all of
don't
them
have to.
together.
Yeah, we don't have to do it right. Wait though. Yeah, we have to wait. I'll just write it down so I can like
Yeah, go for it, mate.
get my
Take
head.
your time.
Okay, if I find x, I can subtract that from 4 to get the other side and use the Pythagorean theorem here again.
Use the yeah. So finding X and then Pythag to get Y. Is that what you mean?
Wait, no, the CD. Wait,
CD.
wait, I'll just,
I'll point
I'll
out.
just
So
do
for
it.
10A specifically, we're just trying to find BC, the top.
Oh, yeah, VC. Yeah, I was,
Yeah. Okay. You're going a bit
um,
further to get. Okay.
okay,
Gotcha.
wait, so, oh yeah, we can just find X then.
Yep.
So, yeah, hmm, because, wait, this, okay, so, X will be cos, um, yeah, cos theta. Wait, no, wait, cos, cos theta will be equal to X over 4, so 4
Yeah.
to the other side, that's X equals to 4 cos theta.
There you go. Yeah. It's a pretty common physics things as well when you do like your projectile motion related stuff. You've got the hypotenuse, which is kind of like your initial vector, and then you split up into the horizontal and vertical components. So it all comes together.
Yep, okay. Yeah, so X is 4 cos theta, so BC will be double that at 8 cos theta.
Yep, that's exactly it. Got those. This translates up to here, and then obviously you're doubling that up. Brilliant. BC 8 cos theta. Done. Next up, find the area of the trapezium and hence maximize it.
Area of the trapezium. Okay.
Mhm.
So yeah, we'll have to find y for this. So
Mhm.
Okay, yeah. So y I guess it's the same. So 4 sine theta.
Yep, that's good.
Okay. Okay, so y that's the height,
Yep, that'll be the height.
and BC and AD those are A and B.
Hmm.
Um, okay, so area of trapezium that's h times a plus b, h of a plus b over 2.
Yeah, yeah, that's right.
Okay, so h of a plus b plus over 2, and so a and b are x and y. Wait, no. Um, a is bc.
Hmm.
You can set a as bc and b as ad.
Yep, B
So
is going to be AD. So far, let's see. So we got our H, which is our Y. So 4 sine theta goes there. We've got the A, which was 8 cos theta. We have AD, which we haven't clarified yet. That's the last thing, I guess, to figure out what's AD.
ad that's 4. 8.
Yes, very good. Recognizing that it came from a circle. And the radius is 4, so that's it. Brilliant. Yeah, that's our full function.
Okay, we can simplify it. So
Yeah, this will be, let's say this is a CAS one.
okay, so um, now 4 sine theta becomes. Okay, so I'll just do it. I'm going to use some product rule.
Yeah,
So
yeah.
there's a 4 sine theta. That's that's one function, and
Hmm.
the other one will be 4 cos theta plus 4.
Yep,
Okay, so derivative of the first function, that's going to be 4 cos theta.
yep,
The derivative of the second one is negative 4 sine theta.
yes. That's it.
Yep, so the product rule, that's u v dash plus b u dash.
Hmm.
It, yeah,
Yeah, that's right. You just go on the diagonals. So, yes, yes. Just double check I did that right. 4 cos, 4 cos. Yeah, 4. Yeah, okay. Does that look?
Um, I'll just work through this.
Yeah, I mean this one, it's definitely doable, tech free. It'll take some strong trig simplifications to get there. If you want to do this one tech active, that's pretty okay. I don't think they require you to do this much tech free.
Okay. Um, yeah, I got the same thing.
Well, that's good. Yep, it's good that you got this far.
Okay, so I guess we just try find that set to 0.
Yeah, yep. Set derivative to 0 and then try to solve. That's where we're going to run into some tech free trouble. Because you're going to have the addition of 3 circular functions.
Yeah.
Just thinking out loud, what kind of things would you try to do if you did have to do this tech free?
Um, so maybe try and convert to 10. But wait, no, that's
Yeah, maybe
still.
dividing everything
Yeah,
by
we
sine
could.
squared. Oh, sorry, divide everything by cos
Cos
squared. Because that would cancel this. That becomes tan 1 over cos. So you knock down to 1, well, 2 circular functions as opposed to 3 now.
Yeah.
Gets there. If you've done if you've done it on the CAS, you'll see that there's also another thing that you could work towards.
I mean, you can take out the 16. That's probably going to simplify it a little bit.
Yeah, so killing all these 16s. That's good.
Um, I can't think of anything else.
Yeah. You actually did bring it up before, which is Pythag. Sine
Yeah,
squared plus
because
cos squared equals 1. So we have similar going on if we do a
yeah,
bit of rearranging.
science method plus cos squared. That's yeah, we can just set that to 1. Wait,
It's not quite yet,
but we
though,
have
because we got plus minus. What I was more
yeah,
so, it's not just going to be a matter of replacing these with 1 or negative 1. It would be getting sine or cos squared on its own and replacing probably the sine squared, because then you've got all coses. So you would do something like sine squared equals 1 minus cos squared, and then rewrite it more or less like, so you're going to have negative bracket 1 minus cos squared for that, a positive cos squared and a cos, positive cos squared, a cos, simplify that down, so you're going to have 2 positive cos squareds, a negative 1 and a positive cos. And here, is that going to be fine? This looks like it should be good. So what's that starting to look more like?
what?
So we got it down to this stage here where we basically
Yeah,
used our Pythag to replace the sine, so now we all have causes in here. The format of this kind of equation is reminiscent of a different kind of function that we know how to solve more so. We use this technique.
quadratics.
Yeah, exactly. Quadratics. So you do some substitution like a is cos, right? You got 2a squared plus a minus 1. Well, now we're just solving a quadratic, however you want to solve that quadratic.
Yeah, so you can do splitting the middle term. So to we have to get two numbers that multiplies into -2 and adds to +1.
Wait, why negative 2
Mhm.
and positive 1?
-2 and the +1.
Wait, what was it?
Multiplies to -2 and adds to +1.
Yeah, but why have the signs flipped?
Um, because 2 times -1, that's -2. Uh, am I not supposed to do it that way?
Well, you're doing the add together times together method, right?
Yeah.
It because you want to multiply for this one. Hang on, am I getting this backwards? I don't usually do it with when there's coefficients out here, so maybe I'm just um, a bit lost on it. Go ahead and do what you're doing.
Okay, so 2 times -1, that's -2. So multiplies into -2 and adds to +1. So that's 2 and -1.
Okay.
So we can just 2a squared uh, plus 2a minus 1a minus a minus 1.
Oh, okay. So you're doing
Yeah.
okay. Now I see what you mean. You're just splitting this up and then doing basically grouping at this point.
Yeah.
Yeah. Okay. Cool. I follow. All right. Let's finish it up then.
Yeah. So we can take out 2a from the first 2 terms and -1 from the second 2 terms, the last 2
Hmm.
terms. And, yeah, we just 2a minus 1 times a plus 1.
Yeah, that's good. Plus 1 equals 0. I'll just speed things along a little bit. A is a half. A is -1. Our substitution was A is cos. So we have cos is half or cos is -1. Let's start with this one. Where does cos go to a half?
Um, pi over 3.
Yep, plus minus pi over 3, those two spots. Probably just going to be the positive one based on what we have as the picture, but just for
Yeah.
completeness sake, we'll get both solutions in there. And cos
And
being
then
-1.
-1, that's pi.
Yeah, that's right. Cool. So that would be within one revolution of the unit circle, which is all we would ever do, right? There's no point going around multiple times. Out of the solutions there, one of those is going to be the minimum and one's going to be the maximum. Because we're doing diff equals 0, it's going to be not necessarily guaranteed to always be the max or the min. This is where I guess I would just refer back to the picture. So which of these seems like the best angle to choose to maximize it?
Um, pi over 3.
Yeah, pi over 3. That's right. Which pretty much is the angle they gave us in the picture,
Yeah. Yeah.
which is nice. Because if you choose pi, actually, what even do you get if you choose pi? Because that means where you choose, yeah, it's just a straight line. Yeah, no area at all.
Okay, so why did we get like
Hmm?
it's going to be basically no area?
Yeah, because BC becomes AD if it's
Yeah.
pi.
So why did we get pi then?
Well, because let's see how we got there. So our whole procedure was we had our function, we did our derivative using product rule, and then we solved derivative equals 0. We did the whole procedure of solving derivative 0, and we got those. So what does derivative equals 0 give you?
Uh, yeah, I think
Yeah, it gives you stationary points, not necessarily the maximum. It'll give you maximums, minimums, and inflection points.
oh
So
yeah, yeah.
yeah,
Okay, I get it. Yeah.
so we saw both, right? We saw what minimum area looked like, 0 area, and we saw what maximum area looked like. Which, now that I'm talking out loud about it, we still haven't quite solved the question. It wanted the maximum area,
Yeah.
not the,
Maximum area.
yeah.
Yeah.
So
Okay. So maximum area,
Mm-hmm.
that's with positive pi over 3.
Yeah.
Okay. Um, yeah, I guess we just applied to the um, area function.
That's it. Yeah. So that was this one here. Let me see if I can get a copy of it. Okay, so for sine pi on 3, for cos pi on 3. So as far as starting to simplify those down, sine pi on
So
3,
4 sine and 3, that's going to be 4 times 3 over root 2. Wait, no, that's
yeah,
root 3 over 2.
other way around, that's good. Yep.
Yeah.
4 root 3 over 2, and cos is going to be similar.
That's going to be 1 over 2.
Yep.
So that's going to just 2. Yeah.
Yeah.
Plus 4.
And yeah, the rest of this is whatever. A equals,
Yeah.
so 4 and 2 are going to cancel into each other. 4 and 2 again cancel, so 2, 6. 12 root 3. Do we have... Yeah, okay, they use units. So let's just say units squared. Sick. Alright. So yeah, that's probably one of the more complicated ones that you'll come across, where they'll chuck trig in there because, well, as you can see, the trig solution does become quite more involved. You've got the actually creating the equation, which probably is like the first level of trig, but then the second level, which is solving the diff equals 0. So we can see this was doable, tech-free. I have yet to see an exam question that'll take it this far as maximizing area is concerned. Though I did see one in a slightly different area of study. I think I brought this one up before, where it was a really complicated logarithm solution set. Doesn't really have too much to do with what we're talking about, but more so in the sense of like how many steps are involved in tech-free. I'll pull that one out just in case I'm making things up and I haven't talked about this yet. This was in one of the, I think this was the 2024 exam. Where is it? You get this, which seems sort of whatever until you realize it's got 4 marks there. So you do your logarithm solution stuff, you end up with a quadratic, a cubic actually, and then you realize, oh shit, now I gotta do your factor theorem related stuff to get there. So you do your factor theorem, then you do your polynomial division, you get your factorizing, then you simplify, and then you check your final answer. So there's precedent for this sheer amount of simplification steps, even in tech free, not just in tech active. So it's good that we were able to go through that. Cool. Okay. What else have we got going on here? Almost done. So let's see if I can find a good one to finish this off with. Oh, actually, this one might be good. It seems fairly simple, but it's a question that doesn't really come up a whole lot in textbooks. Find a point on the parabola that is closest to 3, 0. I think it's worded in a way where you might have to think a bit about it. Or maybe I'm wrong and you've seen it before. One way to find out. Pictures can certainly help if you're fully stuck on what to do. Getting a sketch of the parabola, dotting out the point 30. So just sort of mapping out how far any given point along the quadratic 30 might be. In the real world, if I gave you two things that were similar length to each other, how would you figure out which one was smaller than the other?
Oh, I didn't realize my mic was muted.
Oh,
Okay.
okay.
Um, I was so confused.
You
Okay,
would be
so I
fine,
was
yeah.
thinking of using the Pythagorean theorem to find
Yeah,
the distance between that
that's exactly
and
what you should
finding
do.
the derivative of that.
Yeah, no, that's perfect. You're right on the money there. So maybe the challenge was actually creating the Pythag theorem, or
Um, yeah.
okay, the challenge is in creating it. Sure, sure. Um,
I don't have it memorized. I just try and figure it out whenever I need it because I don't really need it very often.
yeah, no, that's absolutely right. That's sort of why I saw this one because it has come up in multis on exams. It's more common as an exam question than it is in the textbooks. They like to do
Yeah,
areas,
yeah,
volumes, and that sort of thing. Yeah, so distance equation. Distance equation is the same thing as Pythag. It is just a rearranged a squared plus b squared equals c squared, where c is your length. So basically ends up being square root a squared plus b squared. One of these is the horizontal component, the other is the vertical component of the triangle that you're trying to create.
yeah, yeah.
So if we end up creating a basic
Okay.
triangle from that,
So it okay. So the point would go down y, so negative. That would be negative, and x is positive.
positive or negative is going to end up being up to
Dependent. Yeah,
interpretation. It's going to end up
yeah,
being squared anyway, so whether you make it positive
yeah,
or negative is kind of whatever. More so is how we're actually going, like what the actual number or letter involved is. That'll be the most
yeah,
important thing.
yeah.
So it's
Okay, so yeah. Um, hmm. Uh, okay, lost my train of thought.
that's fine.
Okay,
I'll give a little bit of a
so
hint there. So we'll say this is another point that exists on the graph, and that point's going to be the stand-in for the closest spot to 30. Having that defined will be helpful for putting it into our function.
oh yeah, I'm trying to find this the difference between them,
Difference between, yeah, it's going to be a
the 2 points.
difference because this is on the x-axis. You do get a bit of it does become a little bit easier for some parts of it. Like for instance, the vertical component is just going to be whatever the y value is because it's already on the x-axis there. Um, So whatever the y coordinate is, so this is, let's write this properly. So this is going to be q x comma y, just some x and some y coordinate. This bit here would therefore be x. As far as now transferring things in, the vertical component will be the first and easiest thing to put in there. So we've got a squared, which is going to be like the vertical component squared. What are we going to put in there?
Okay, we can put the x values, so x2 minus x1.
X2 take x1, yeah. So 3 take x in that bit, are you talking about?
Yep.
Yeah, perfect. So 3 take x, and that'll be all squared because of the Pythag part. And there's a plus between them. So that'll be the horizontal component. Vertical component's going to
The
be,
horizontal, that's negative values, so 0 minus y.
yeah,
So that's negative y.
yeah, negative y or positive y. It's going to be squared either way.
Yeah, it doesn't really matter.
Cool. So that gets us most of our distance equation with, one slight problem, which is that we have both x and y in it.
Yeah.
So the next goal is quite natural, which is going to be how we're going to remove the y or the x if you wanted to. We just need one variable.
We can replace y with x squared.
Replace y with x, that is correct. Nice. That was going to be y squared, which is now x squared squared, so x4. Sweet. We got our distance equation, and the rest of what you said now just sort of, we follow the procedure, just like you mentioned. Derivative
Yep.
equals 0, that sort of thing. This one's going to be a bit interesting. So as far as diffing this, what kinds of things will we start to do?
That's separated into two functions, so square root of a function. That's how I'm thinking of doing it. Yeah.
Yeah,
So
okay.
that's going to be 3 minus x double squared plus x to the fourth.
We're chain ruling it, nice.
Yeah. So 3 minus x. Okay, so I'll just do the top one first. So that's 2, sorry, no, 1 over 2 square root of u.
Yep, perfect.
Yep. Okay. So u dash. So the first term there, that's 3 minus x whole squared. So, 2 of 3 minus x times negative x.
Are you trying to chain rule that?
Yeah.
It wouldn't be negative x, it'd be probably negative 1 because it's a diff of the inside.
Oh yeah, negative 1.
Yeah.
Negative 1, yeah. That's what I was thinking, but I said something else.
Yeah, no, I getcha. So
Yeah.
the 2 goes out the front, the negative comes out the front, and then you just got 3 minus x left over because that's reduced by 1. And, well, x to the 4, that's the easy one.
3x, 4x to the third. Yeah.
Yeah. Maybe just clean things up a little bit. So that'll be 2x from that minus 6, 4x cubed. Yeah. Sweet. Getting there. I have a suspicion this will be fun.
Wait. Oh yeah, that's negative. Okay. Got it. Yeah. Yeah. Now we just do the chain rule again on the inner and outer functions.
chain ruler. Oh, as in like
Wait,
finish it up?
yeah,
Yeah,
finish.
yeah, yeah. Cool. Yep, so multiplying those two diffs together. So we're going to have, maybe let's write this in order this time. 4x cubed plus 2x minus 6 is the first bit, multiplied by 1 over 2 root u, where u is, oh god, yeah, okay. Maybe we'll expand that out. So we'll have the x4, we'll have an x squared, we'll have minus 6x, and we'll have a plus 9. So that's our diff. Is this going to be too awful? Can this ever go to 0? Maybe. Point being, this is certainly going to be a tech active one to finish this one up. The reason why
Yeah.
I'm hesitating to just like multiply both sides by the denominator is the denominator might be able to go to 0. Really hard to see just by looking at that polynomial whether there's going to be a solution for 0 on that. You could test, of course, but that seems a bit ridiculous. Actually, sorry, no. Multiplying both sides by denominator should be fine. Because it's only divide by 0 that's the issue. Yeah, oh, never mind. This will simplify down to just 4x cubed plus 2x minus 6. And then, yeah, divide everything by 2 again. And then I guess, yeah, doing the factor theorem stuff that we saw in the example that I just brought up before from the exam solution set. So I'm talking high level because we're about to get time on this. Is it clear enough how you would then like follow the procedure from there on?
Yeah.
Yeah, sweet. So cancelling that out. Is there going to be any issues? Well, we know x is going to be a positive, so if you do, for whatever reason, get into a plus-minus situation, you know it's going to be plus. You're going to get the x value, which would be that. But because it says find the point, you also want whatever the y coordinate is at that spot as well. You'll probably only ever get one solution to this because maximum distance is going to be infinity, right? If you're looking for distance from here to quadratic, you're probably only going to get the minimum. I don't think you will hit a max because it's got to be infinity.
Yeah.
But cool. Okay. Sweet. Maybe that'll be a good one to finish up on your own if you were working on that solution. What I can do, if you do want to finish that up, let me know and I'll send you the solution PDF for this so you can compare your answer at the end if you like. Just let me know over school or I think you got my number as well.
Yeah.
Sweet. Anything further to clarify?
No. Wait, just one thing.
Yeah.
Since I'm the only one here, can we talk a little bit about like private key thing?
Yeah, certainly.